Hey, it's Mr. K doing a video for AP Physics C and 1 as well. We're going to talk about something called the universal law of gravitation. We're also going to throw in a little bit of centripetal force in there because wherever you find universal law, you probably have some centripetal force involved as well. But let's go ahead and start with that. Let's start with a problem that you should know relatively well, or it is relatively simple in our grand scheme of things. Let's say that we have ourselves and we are just standing on the surface of the planet. So we're just here, I'm sitting here, this is me, and let's say my mass is like, I just make it easy, 50 kilograms. It's more than that, by the way. Let's say my mass is 50 kilograms, and let's figure out the forces on us. So the forces on us, free body diagram, do a dot, and let me have a force downwards, which is the force of gravity. We'll call it mg, and then we have another force on us, which is called normal force, pushing back up because we are pushing into the ground. These are not third law forces, all right? If we take away the ground, the force of gravity still exists. So this normal force is because we're pushing into the ground, and these two should equal out and cancel each other out. We should be in equilibrium at that point. mg is going to be 50 times g. Let's make g about 10, and that will give us about 500 newtons of force that we are being pulled down with, which is the force of gravity on us. Normal force would therefore have to be about 500 newtons in order for us not to accelerate. So that's the simplified version of it. There's another equation for the force of gravity, which is the true equation of the force of gravity between any two objects, and that is what we're going to introduce here. So Isaac Newton discovered this guy, and came up with. Anyways, here it is. It's big G. Big G is a constant, universal gravitational constant. We have m1, m2 divided by r squared. And m1 and m2 are two masses that we care about. So right now, it would be me, 50 kilogram me, lighter me, and the other mass that's pulling us down, which would be the Earth. So you don't always have to pick the Earth and you. You can pick these two pens. These two pens have mass, and they would be gravitationally attracted towards each other. But the major force here is the force of gravity between the pens and the Earth, so we don't really notice that they're being pulled together ever so slightly. And they would accelerate if they were the only things in space and they were sitting about yay far apart. You would eventually get them to come together. But on to this equation. So G is going to be a constant, and it is 6.67 times 10 to the negative 11th, and it's got some weird units. Newton meters squared over kilograms squared. And I only say they're weird because a lot of times when you just look at a mixture of a jumble of units like that, you're not really sure why they're there. But if we take a look at the equation, if G has units of this stuff, look at M and M. Those would have units of kilograms, so that would be kilograms squared. And then R would have units of meters. That's actually distance, like distance between these two objects. And that would be squared as well. So if you notice, we have meters squared on top and kilograms squared on the bottom in this constant. And then here we have kilograms squared on top and meters squared on the bottom in this equation. And those would cancel each other out, giving us just newtons. So there's usually a good reason why the units for these weird physical constants exist. And it comes down to figuring out the ratio of things and making sure that our units are actually correct for our equations. So let's do a quick one. Let's go ahead and look at this equation for us. Okay. So if I want to figure out me, I can have the force of gravity on me, and that's equal to G 6.67 times 10 to the negative 11th. And then I'm going to say, all right, what's my mass? I'm going to be m1 in this case, 50. I'm going to say, what's the mass of Earth? The mass of Earth is a bit big. It's going to be 5.972 times 10 to the 24th kilograms. Okay, it's pretty large. That's the mass of the Earth. And then we're going to divide this by the radius of the Earth because we're standing on top of it. 1 radii away from the center. And so we're going to put in the radius of the Earth here. That's going to be 6.378 million, so times 10 to the 6th. And then that's going to be squared in the bottom. So this is where it's going to be really important to use parentheses. If you're typing everything into a calculator, you really should use parentheses. If you've got a TI-84, 83, or whatever, use parentheses. I use a TI-30. just because I found myself losing math skills when I was using TI 84s or 89s. So I just kind of forced myself to use the TI 30. So let's see. TI 30 would say, let's go ahead and multiply across the top. 6.67 times 10 to the negative 11th. Okay, so there you are. We're going to start off with that guy. We're going to multiply by 50. We're going to multiply by 5.972 times 10 to the, what was it, 24th. And I'll hit enter there. That gives me this number. We're not done with it yet. Okay, we need to divide by, and here I'll use a parentheses definitely, 6.378 times 10 to the 6th power, and we got to square all that on the bottom. So if we did it right, then we get a force on us, which is about 4.89 times, wait, what do we got? 489.6 newtons. Well, that's not 500. That's kind of weird. Why is that not 500? And let's not forget that we often round our acceleration due to gravity from 9.8 to 10. What if we used around 9.8? 50 times, not 10, but 9.81 or 9.8. And we get closer to 490. And so this is really about 490 newtons. And that's good because we're actually using the constant 9.8 as we should instead of just rounding it up to 10 like we usually do. And that fits the actual gravitational equation here. So, you know, we're being pulled down with this amount of force. We're also pulling the Earth up with the same amount of force. You know, we can just switch these masses and it's still multiplying and getting the same answer. Okay, so Newton's third law would say, hey, if gravity is pulling us down, we're also going to pull the Earth up with the same amount of force. But the mass is a bit different. So if we know that this is the formula for, again, the force of gravity on us, let me just show you one more thing. G, M, us, M, Earth, divided by radius of Earth, and that's going to be squared. If we were to look at this, and I just kind of move some things around, G, M, Earth, M, us, divided by radius of Earth squared. Didn't do a whole lot of moving, okay? But I want you to notice that all this stuff here, it's going to be a mess of numbers. What we do is we simplify it and we say, hey, we're just going to call that little g, and then we're just going to multiply by the mass of us. And that's where we get the whole mg thing from. So mg is a shortcut instead of using this equation all the time to figure out the force of gravity on an object. Okay, so this is only true if we're just on the surface of Earth. As we get farther away from it, or if we go to a different planet, then that's probably going to change. That g value is going to change. So that would be the attraction between any two objects. You can put any objects in there. You can say it's us, and it's the person that's sitting next to you. Is there a force of attraction between you two? There is. It's called the force of gravity. All right, it might be really small, though. So let's keep that in the back burner for the moment. Now, we have things that are always being pulled by gravity, and they're in space. They're orbiting. And so if we were to do something like this, let's say we have a kind of large circle. We're going to call this, can I make it all the way around? I don't know. There we go. Let's call this the planet. So this is Earth. And we have a satellite out here, something out here, just kind of buzzing around. And that thing's going around in orbit, in a nice circular orbit. There are multiple kinds of orbits. So you can have like an oval, you can have one that goes way, way, way out, a big ellipse and comes back in. Let's just call it a circular orbit though. So this satellite, which is a circular orbit, ooh, can I do it? Is going to go like this, deet, 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 all the way around. And it's going to be in a circle. And it's falling the entire time. And if we were to draw a free body diagram for that satellite, I would draw a force on that satellite that points towards the center of the planet, and that would be the force of gravity at that position. Now, it's not going to be just mg because we are pretty far, we're farther away from the center of the planet. All right? And so the force on the Earth is the exact same. We're pulling the Earth towards the satellite. These two forces are the exact same amount, Fg. Okay? And so my question to you would be, you know, how much force is on the satellite, what's going on with the satellite. It's also moving in a circle. So, do forces move things in circles? And the answer is yeah, they do. So, what do forces do before we move on? Forces, remember, F is equal to ma. Really, it's the sum of all forces is equal to ma. Forces cause accelerations. Unbalanced forces do. And so, what is an acceleration? Acceleration, at its base definition, is a change in velocity over a change in time. How do you change velocity? Right? You can increase it, speed up. You can decrease it. You can slow down. You can change its direction, and that's called turning. So what we're going to do here is we're actually going to use an acceleration caused by this force of gravity, because if you look, the force of gravity is the only force on it, right? If this thing wasn't moving to the side, it would just fall straight down to the planet, but it is moving to the side. And so this force of gravity is causing it to turn. And that is called a special thing called a centripetal force. So a centripetal, not centrifugal, but centripetal force is a force used for turning. So, used for turning. And that force that's used for turning, it points perpendicular to the motion of the object. Okay? Forces that are used to speed us up point in the direction that we're going. Forces that are used to slow us down point opposite the direction that we're going. If I do this with my pen, okay, on the way up, gravity points down, thing slows down. On the way down, gravity points down, thing speeds up. So centripetal force is going to be a force that points not forward, not backward with the motion, but perpendicular to it. Okay? So here, if you look, my object is moving at the moment in this direction. But gravity is perpendicular to that, pulling it back towards that surface. It's going to turn us the entire time. 1 second later, this object might be over here. Gravity still points towards the center of the planet, and the velocity has changed, and it's still perpendicular. So this thing called a centripetal force is used to turn you. So centripetal force, I want to say Fc, is equal to mv squared over r. And let's make this make a little bit of sense. You're in a car, and you take a right turn real quick. Well, if you take a tight turn, you feel like you're being thrown out of that turn. You feel the force turning you. It's not really that. All right, it's your body's inertia trying to fly out in the same direction that it was. Your car, hopefully just your seatbelt, but maybe your door is what's going to push on you to make you turn in that direction. The faster you go around the turn, the harder it is to keep in that turn itself. If you run and you take a quick right turn around a corner, you can feel it. Like your body wants to keep on going in the same direction, but your ankles need to your feet need to put that force down on the ground to make you turn into that turn. Okay. But if you want to take an easier turn, you make the turn bigger. You make R bigger, all right? Or you slow down. Usually whenever you're learning how to drive, if you're taking a turn, you hit the brakes a little bit to make it easier for your car to take that turn. The faster you go, the harder it is. The more massive your car is, the harder it is to do that. And especially on a rainy or a icy day, you might slip out because friction is what you're using to help you turn. Okay, we're going to look at that after we do this one. So with centripetal force is is going to help us turn, and here the centripetal force is already in the problem. You never draw a new force for the centripetal force. It's always already there. And so the force that's turning us is going to be the force of gravity. Here we are. So the centripetal force is the force of gravity in this problem. Centripetal force is mv squared divided by r. Force of gravity on this problem is big G. M, we're going to call it M satellite. M, Earth, the thing that's pulling it towards it. And then we have divided by r squared, this distance away from the center of the circle that I'm turning in, which would be the distance to the center of the Earth from wherever the satellite is. So now let's do a little bit of algebra. This M over here, what is it? It's the mass of the thing going in the circle. It's mass of the satellite. So if I look here, algebra-wise, you see how we can just cancel out the mass of the satellite? That's kind of neat, because it helps if the mass of the thing moving in orbit doesn't really matter. That means we can put a bunch of different sized objects in the same orbital path, like a space station, and they don't fly apart. They all just stay together. Another thing we can cancel out is one of these r's. This r goes away. One of the r squareds goes away, so it's just r left over. And let's clean this up just a little bit. So we got v squared is equal to g, the mass of the Earth, divided by the radius that we are currently at away from the center of the planet. And so if you want to figure out how fast your satellite needs to be moving in order to achieve orbit, you just square root the right side, knowing what altitude or what distance you are away from the center of the planet. Okay? If you want to figure out how fast you need to be moving at the surface of the planet to just orbit around at the surface of the planet given no air resistance, you just put in the mass of the Earth and the radius of the Earth and square root that times g. Square rooted. It turns out you got to move pretty fast. So let's talk about centripetal force a little bit more. Let's do one more problem. Let's do that car problem that we were talking about. So let's say that we are looking down on a car, and this car is right here. And so we're looking down on the car. So it's a big rectangle. And I guess we can maybe see some tires out on the side. Okay. And so this car wants to take a turn. And this turn, use a different color. So this car wants to take a turn, kind of looks like this. All right. This turn's got a certain radius to it. Say it goes like here. That's the radius of the turn. You're on a typical road. We're on Broad Street. You're going to take a right turn from Broad Street onto Matlock, and that turn's radius, let's make it 10 meters. Okay, that's a number that we're kind of used to. So that's going to be a 10-meter turn, 10-meter radius turn. We got a car. Let's say the car is, I don't know, a ton. So maybe 1,000 kilograms, 2,000 kilograms, pretty heavy. Let's just call it 1,000. 1,000 kilograms. And how fast would you be taking this turn? Well, if you're a teen, you're probably taking it faster. So you're probably going around 45 miles per hour on Broad Street. You're probably going faster than that, honestly. And let's say you're taking this turn with a velocity of like 20 meters per second. Okay? And so you take this turn. And in order to turn, I guess this would be a left turn or right, I don't know. So right turn if you're coming towards the school from like 287. And car's moving this way. And let's figure out what's going on with this stuff. So we got the centripetal force need is going to be Fc. That's going to be mv squared over r. The mass of the car is going to be 1,000. The velocity of the car is 20, square it, divided by the radius of the turn, which is going to be 10 meters. Okay, so if I look, 10 is going to cancel out one of those zeros. It gives me 100. 20 squared is going to be about 400. So if I look at that, 400, there are 4 zeros there. So let's see, 4, 1, 2, 3, 4. That's going to be 40,000 newtons is required to turn us. I was off the page. I'm sorry. So about 40,000 newtons is required to take this turn. Now, what are we going to use to take the turn? You know, and it has to be a force between the tires and the ground. We're going to use friction. So friction has to point in towards the center of the circle. That is the force that's making us turn. That is the centripetal force. Again, we're not going to draw a new force that is the centripetal force. It's already going to be on our problem. So centripetal force is force of friction, and force of friction has to be at least 40,000 newtons. Well, what is the force of friction's equation? Force of friction is normal force times mu, some coefficient of friction. Well, right now, if we know that we need at least 40,000 newtons, I can set 40,000 equal to normal force. Well, what's normal force? We're on flat ground. So normal force is mg. M being 1,000, g being 10, so we're going to call it 10,000. Okay? And then mu is this coefficient of friction that we need between the tires and the ground. So I'm going to look again. I got a little bit of math to do. I got 1, 2, 3, 4 zeros there. I got 1, 2, 3, 4 zeros there. And so my mu coefficient, we're going to call it static friction, has to be at least 4. What does that mean? That means that it can't be done, probably. Most coefficients of friction are between like maybe 0.5, 0.8, 1.5 maybe. But to have a coefficient of friction of 4 is like maybe your tires are made out of Velcro and they're sticking to the road. That's a lot. So you might want to slow down on that turn, or else you're going to spin out. If it's a 10-meter turn, if the turn is more than 10 meters, then you're probably all right. But for right now, that's a 20-minute video, so I'm going to stop it here, and we will move on.